All right. Order. Let's get started. Well, welcome to the last Swarm Lab seminar of the semester. So it's been a good semester. We've had a lot of great talks, and we're really pleased to have a representative from Qualcomm here today as our last talk of the semester. We have Payam Pakzad from Qualcomm. I'll tell you a bit about him before we get started. Also, I wanted to welcome people from the Software Defined Buildings group are visiting with us today, as we all have a lot of interest in indoor localization. So this is really great. So Payam received his BS in Electrical Engineering and Applied Mathematics from Caltech in 1998 and PhD from the EECS department at UC Berkeley in 2004. He was later a postdoctoral researcher at EFPL in Switzerland, where he worked on low-complexity error-correcting codes. Payam was with Digital Fountain from 2006 to 2009, where he was a senior researcher on design and applications for fountain codes for video streaming over the Internet. He joined Qualcomm Research Silicon Valley in 2009, has been a technical lead for Qualcomm Precise Indoor Positioning Solution. Payam has over 25 journal and conference papers and has over 20 granted and pending patents on various topics in information theory, error-correcting codes, graphical models, network coding, video streaming, and indoor and outdoor positioning systems. So we are very excited to hear your talk. This is a subject that is of great interest to us. So thank you for coming.
Thank you. So I should first, give a little bit of warning that first, this project, at least the research aspect of it, has been around in Qualcomm for the last few years, and some of you might have heard a version of this talk. Actually, I know for a fact that a colleague of mine, Ravi Palanki, last year gave a version of this talk, and myself a few weeks ago at BWRC. So I hope that I can provide some more updates for those who have heard this talk before. But let's get into it. So the first of all, I wanted to kind of motivate a little bit why it is that we are interested in this problem. So obviously, when we're talking about indoor positioning and navigation, you're not talking about how to get from your bedroom to bathroom in your house, at least not in most of our houses. But in any case, what we're interested in is kind of larger venues and the kind of applications that this technology can provide. So this slide summarizes a few of the applications that you can imagine. There's a whole aspect of this, which is how to enable new services and applications given this technology. But let me just enumerate a few of these applications. So first of all, for example, we're talking about really precise kind of positioning. This is few meter level accuracy, which allows you to have turn-by-turn navigation for a pedestrian in an indoor environment. If you're in a mall, this would be able to tell you whether you're in front of this store or the next store a few meters away. Or within, for example, a grocery store, this would give you, check-in ability at the aisle level. Or, for example, you could be looking for, milk in Safeway, and this would be able to tell you that you're in front of it or go two aisles next to it. This technology enables you to have content and media that's very relevant to the place and position that you're at. So you can imagine, again, that depending on where you are, you would be able to get video background or some information. In a museum, for example, you're standing in front of a piece of art. This would give you, for example, information about the work and so on and so forth. Seamless indoor and outdoor tracking of the person. So you're walking from outdoor into an indoor mall. You would be able to, for example, without any interruption, continue tracking your position. And what's more, you could, for example, enable, if you're going with a group, friends or family, into a mall, you could be tracking the other people, know exactly where you are relative to the other people. Another example is, you're driving into an indoor garage. GPS just doesn't have, in an indoor environment, that kind of resolution to give you the precise position. You could, for example, mark the place that your car is parked, and later, if you're walking to the car, give exact navigation instructions, how to get back to your car, and so on. And finally, you could have incentives that are based on the location. So, for example, in a casino, if you're in the main lobby, for example, this could give you. The owner could incentivize you. Right now, there aren't that many people in the slot machine, for example, area. $10 free chips if you go to that area in the next 5 minutes. So obviously you can extend these kind of applications. The limits is really your imagination. Once you have this kind of technology, you can imagine what set of new services and applications would be enabled. So the way I described it, this is like really a hard problem. There are a lot of different aspects to this. For one thing, if you're outdoors, you're relying on, for example, GPS. GPS satellite positions, these are information that are once and for all set for pretty much anybody in a very large area that you would be interested in. For indoors, this is not going to be the case. You need to rely on information that are assistance data that are related, very specific to the venue that you're in, to the world that you're trying to map yourself in. So it's important to be able to tell automatically when you're entering a new building and to be able to download or pre-set up the system to do positioning in that new venue. Along the same lines, seamless floor determination. If you're going from one floor to the next, you need to be able to know this so that you update the assistance data for that specific floor. And same thing as transitions between indoor and outdoor. And again, the reason this is important is that there are situations, for example, that you're concerned about power. Outdoors, GPS signals make a lot of sense. They give you some good estimate of the position. In the indoor, even if you do get some signals, which I'll talk about it in a little bit, why it's a hard problem, even if you do get it, they're pretty much of very little use. So if you for the power reasons, you really need to know whether you're inside or outside. You may be able to, for example, switch between different types of positioning. Outdoors, Wi-Fi doesn't make sense. Indoors, GPS doesn't make sense. Sometimes if you have precise enough positioning, you may want to turn off sensors and so on. And another aspect that I spent a little bit of time before was the services and applications. There is like a whole new area. Once you have the technology, you can imagine what kind of new services you can enable and the markets and so on. There's like all the research. And finally, the actual technical aspect of this, of how to do positioning, how to integrate different sources of information, and how to give the best location that you can in an indoor environment. And for the purpose of this talk, actually, I'm going to just focus on the last aspect. So all of those other things, we're going to assume that they are pretty much solved. Okay, so you assume that you already know what world you're in, which floor you're in, and so on. And as you can imagine, obviously you can imagine, those are all very hard problems that to be able to determine, for example, to set up the infrastructure and to be able to determine where you are based on the limited information that you have is a hard problem. But again, we're going to focus for this talk on the situation that you've solved those problems. You know that you walked into, for example, this particular floor of this building, and how to use the available source of information and get good estimates in that scenario. So why is this a hard problem? So in the outdoor, again, in the last 10, 15 years, people have been so used to just turning on your phone or GPS and you know exactly where you are to good enough resolution. You can do, you might think that you can always do trilateration and get your position if you have range or distance information, good enough range or distance information from some known reference points. So this thing is really like a cartoon of 3 access points that are, or beacons. They are, you know the XY positions of each one of them, and you're trying to determine the position of the mobile. If you know the distance from each one of these, then obviously you can do trilateration, get, unambiguously get your position. Now, in situations that we are interested in, many of these assumptions are not going to be holding anymore. In particular, you can't assume that you have perfect range estimate anymore. In the indoor environment in particular, you have a lot of multi-path. There are errors. You just cannot have models that are precise enough that give you the kind of accuracy that you're interested in. So what you have to do really is that you end up with a situation that if you try to determine deterministically your position, you end up in trouble because you could really be off. The models are not matching and so on. So what you really need to do is to develop a probabilistic framework that you keep track of the distribution of the location, and this allows you to kind of recover from errors at some instant at a later time, as long as you have information that averages the previous errors, including, for example, routing information and so on. What's more is that sometimes you just don't have enough measurements. If you want to just rely on Wi-Fi or range measurements, sometimes you just don't have it. You want to be able to still have a good estimate, at least in over time. You want to have a good estimate. And finally, the assumption about knowing the position of the access points can be out of the window. So, you walk into a new building, you just don't know anything about this. This is a situation that you really want to do SLAM, the simultaneous locationing and mapping at the same time. You don't know anything about the building or very few things about the building, and you try to recover the information that you're missing and be able to still get reasonable estimates of the position. So back to the GPS case. So like I mentioned, in the outdoor, this problem is pretty much solved. It's very low infrastructure setup that's needed. Once and for all is done, and everybody's happy pretty much. For the indoor situation, this is not going to work for 2 reasons. One is that in most buildings, depending on the type of the material used in the building, you may or may not get any signal at all. And if you do get it, what you get may be completely unreasonable estimate of the position. So in the deep indoor scenarios, the GPS measurements are completely useless. You just don't have enough to work with to get the resolution that you want. And the other point is that even in the outdoor, the resolution that you get for the GPS fixes may make sense quite a bit for the auto navigation case. For example, a 10-15 meter inaccuracy in the outdoor is quite acceptable because in a blink of an eye, you're just getting to that point, to the next intersection. So this is really something that you don't need that kind of more accuracy than that. For indoor, this is not the case. As I mentioned before, you really need a couple of meters of accuracy to be able to enable some of the applications that I was mentioning. So what we have to do is essentially put everything absolutely that has to do with the position, that you can infer the position together to recover from the fact that you just not, any single one of them is not enough to give you the position. So the solution that we are working with at Qualcomm is looking at some of these sources that I've listed here. There are some more that we can talk about later, but here are the kind of prime candidates. The first is Wi-Fi measurements. Obviously, this is like kind of what replaces the GPS measurements in the outdoors. You're getting range estimates from a fixed position. And for the indoor, the thing that makes sense is some beacon in form of the already deployed access points that's pretty much fixed in the buildings, and you can kind of piggyback on top of this existing infrastructure and be able to do positioning using those things. Now, you can use pretty much any other kind of beacon for this purpose. It could be audio. It could be, like some small, very specific hardware that you use just for getting the range information. But really, what makes this solution a little bit, more useful is that if you don't have to go in every new venue that you need to do positioning in and have to install a lot of new hardware. So that's why we wanted to basically start with a already existing framework, already existing infrastructure in terms of the access points that are already out there. The next source of information that you can use is the building maps. If you have information about the maps, obviously you can use this to refine your positioning or improve the positioning, and in many cases actually this makes the difference between getting a useful versus a useful positioning in the range that we're interested in, as opposed to something that is not good enough. Building maps you can use in two ways, at least. I'll talk about it a little bit in more details later on, but you can either use it in terms of the routing information, how the user is allowed to move within the constraints of the map. There's walls here and so on. You can't just jump across the walls. And also you can use it to improve the Wi-Fi models that you use for the first parts. Because if you know, for example, that there's a line of sight view to some access point, this is obviously information that you can use as opposed to something that has to go through walls or different obstructions. And the last part that I'm going to talk about is sensor measurements. These are inertial sensors, accelerometer, gyroscope, as well as magnetometer. And these measurements are going to be different in a sense that they give you the relative motion. You can use this in kind of a pedestrian reckoning scenario. You start with a known position. You can extend the position. This basically helps you to determine the motion, which obviously is a big important part of how to determine the trajectory. So putting all of these together, you end up with a block diagram of this sort. Indicated Wi-Fi measurements coming in terms of signal strength and time of flight. Maps that give you the assistance data, as I mentioned. This could include, again, part of this is location of access points and other information that are fixed for the venue. And then sensor measurements that come in terms of odometry information. And at the heart of this is the trajectory estimation part that puts all of this together and gives you the position. You have a? That's right. No, so actually there is, what we're using is there is in the 802.11 protocol, there is this RTS CTS thing that you can just request to send then the access point immediately without being associated with the access point. They will the access point will send the acknowledgement back, and we use that. This is like a very low overhead communication without having to be connected to the device. But yeah, that's a good point. Okay, so for the rest of this talk, I'm going to be talking about each of these components here, these 4 components, and some detail, probably not much, but in any case, I'm going to be around if you like to chat about it. I can provide some more details probably, but. So I'll get into it in a couple of slides. Okay. So there are a couple of ways that you can do, form a Wi-Fi model, but I'll get to that in a second. Okay. So Wi-Fi measurements, we just mentioned there are 2 types of measurements that you can use in the same, exchange of packets. Receive signal strength indicator, which is an indication of, the strength of the signal. Obviously, the farther you are from the source, signal attenuates, and you can use the correlation between the distance and the strength to estimate the distance from the access points. With round trip time, you're trying to estimate the time of flight, and obviously again this is related to how far you are from the source. Farther you are, it takes longer time. So the first part, the Rssi, pretty much any radio chip, they have a way to do this. There's like this easy enough to do to get the signal strength. With RTT, this really needs specific hardware, design to do this. You're talking about kind of few nanoseconds of resolution that we need. Like about 10 nanoseconds corresponds to about 3 meters of accuracy. So this is something that has to be done at the hardware level, and this is something that Qualcomm is using as kind of distinguishing feature in the solution that we're using. But I'll have a little bit more to say about that. So again, about the RTT measurements, what we do is pretty much what you would have thought that we do. We send a packet and mark the time that the packet is left, and wait for the acknowledgement to come back. And what you're measuring is essentially twice the time of flight, which is the quantity we're trying to estimate, plus some processing delay. The processing delay comes in terms of delays both at the sender and the receiver to do the measurements, get the absorb the packet and form the acknowledgement, send it back, and so on. So for this whole thing to work, you really need this processing delay to be deterministic, or be able to somehow get it within the resolution that doesn't disturb the whole quantity that you're trying to measure, which is that time of flight. And again, like I mentioned, for this to work, for the processing delay to be deterministic, as I mentioned, this cannot be done in software. You really need the access points to have hardware mag. This has to be done, something that it's fixed within a certain range that you can tolerate. Otherwise, this whole thing is going to be. Please.
So, if you do time synchronization, precision time for a photo like a 1588, you don't need processing delay.
It's maybe, yeah.
And there's lots of reasons to do that. Is anyone looking at doing that?
Not that I know of. So at least so I'll tell you that there are different parts to this problem that I mentioned. The actual measurements of the signal, I'm not involved with that. So as far as I know, the reason people wanted to stick with this, the 8211, the existing, the RTS, CTS kind of doing things, was that they want to be enabling the venues that are already existing and have with the kind of legacy type hardware and so on. So that's definitely, if there's a way to improve this measure, the quality of this estimate that you're getting, I think people will be very interested. Yes. Yeah. Yes, yeah. So actually, let me just go to the next slide, because that's exactly what you're pointing at. So, so in a case that you don't have any interference, what you get is, like I said, it just you send the packet, it goes straight line of sight, come back, and you're measuring the direct distance between the two sender and receiver. In the real scenario, if you have an underlying map with obstructions, as you mentioned, what you get is the path of flight for the signal is most likely not the straight path. So what you're measuring includes some inaccuracies because of that. So what you're really measuring is the distance, I mean, kind of its time of flight along something that's not really the straight line. And this is, the source of error in the estimate that you really have to be able to model or compensate for. So what we do is we model the round trip time, the measured quantity, as really something that's related to the direct distance. This is the the actual distance between the 2 points, plus some processing delay that I mentioned, and some errors. Errors come in terms of it's basically a combination of multipath and as well as device and access point timing errors. And for this again to work, you really have to have a good handle on what the multipath component is going to be, as well as be able to estimate the other components. But there are 2 ways to address this. Actually, come in terms of how you're modeling the expected round trip time at a given position. I'll talk about it in a little bit. One way to do this would be to just try to get kind of a radially symmetric, assume a radially symmetric, very simple couple of parameter model. But you can do better than that. You can do try to infer something from the map. And this kind of situation, given that you have the location of access, the access point location as well as your probe location, you can figure out, at least theoretically, how much of a multipath would exist in this particular transmission. But I'll talk about it a little bit more coming up. So the Wi-Fi model is basically the mechanism that takes that measurement and converts it to a distribution over the locations or ranges relative to that access point location. What we do is really, in the absence of anything fancy, we just are using some Gaussian distribution. We assume that you have the measurement is made. You have some expected value of what you expect that signal to be, and you come up with some, depending again on the type of the building, come up with some idea of what the variance is going to be in the measurement. And basically you convert, as I said, the actual measurement to the locations in this way. And as I just mentioned, you can use for estimating that expected value of this Wi-Fi signal, you can use either a simple ranging model that's has only a couple of parameters and is completely radially symmetric, or you can have a more complicated heat map that looks at the map of the building and tries to infer those information. For the RTT, the simple thing to do would be just to assume time of flight plus some processing delay. Now the factor 2 here assumes that you have obviously going straight line going there and coming back. We can do better than that even in this simple case, because depending on the type of the building, it turns out that you can pick these 2 parameters, play with the constant form and the actual factor to fit better to the expected flight type inside that building. So for example, if you have a very open area, this factor is most likely going to be 2 really, because it's a kind of line of sight situation. If you have a obstructed very dense office building, you can, again, by playing with this, you can improve the average performance. And it turns out that if you have enough measurements, obviously you can compensate for some of this error. Yes? Yeah, so that's actually good. So the whole architecture to enable these things is something, a different aspect of this. I'm not going to get too much into it, but the solution that Qualcomm is advocating right now is that there is a server that's serving this information. The assistance data is coming. Once you determine that you're in this building, you download. This is not like a huge amount of data. It's like probably like an order of a few kilobytes. of information, assistance data that you download there, and you can use it. That's absolutely right. Yes, yes. Exactly, yes, yes. So we start with some, okay, I have to say that, the solution that relies heavily on a survey is not really preferred, because you're talking about tens of thousands of venues, like malls and casinos and airports and whatnot. And it really is impractical to have to go and do surveys. So we start with some, binning each type of the building into one of the few possibilities. And we start with some, a priori estimate of the multipath, if you're going with the heat map model. Again, the distinction between the two models comes in terms of, for example, what kind of capability the device has in terms of both, calculating, calculation capabilities, as well as, the download restrictions, if there are any. Yeah, so the heat map, like you said, it can be either pre-calculated via survey or from known models based on what you know about the map. Yeah. So that's absolutely possible. But like I said, it becomes if you're sending people before enabling to, survey the building, that becomes like a big task by itself. But you're doing some crowdsourcing solutions to basically do things that I mentioned at the beginning. You walk into a new building. It's actually a very interesting problem because, for those who haven't looked at this problem, you can do a lot of things without knowing anything at all. As long as you know, for example, what you're measuring are from fixed location access point that you don't know, the access point is not moving around. If you can determine that, then there is enough, correlation in the measurements that you're making that you can, with enough number of measurements at different locations, you can both determine the location of the access points or the fixed points, and obviously from that point on determine your own location. Yes.
How does this compare to the Google Maps navigation, which actually does well, in some cases has to do around what can I see, what can I hear?
Yeah, so I can't comment too much about what exactly they're doing. From what I have seen, they're not using the map in a sense of, the map is a context for where you're walking. They're not using the map for positioning or for calculating the Wi-Fi models per se. Google Map, you get a dot. It depends really on the venue to venue. I think it's different, but from what I understand, again, it seems like what they're doing is just looking at single point fixes based on individual measurements and matching with the surveyed table to get a position. We're doing quite a bit of stuff on top of that. I'm sure Google is looking at similar ideas, but I can't really comment on what. Yes. How consistent? Are you talking about the measurements? How consistent they are at the same time? Yeah. So it's with RTT actually it's pretty consistent, given the fact that so with RSSI I should start that way, because RSSI, depending on what kind of obstructions there are, actually depending on the time of the day and the how many people are in the corridor and doors that are open and so on, few dBs up and down is really is not uncommon. RTT is more stable, especially in the cases that that you have line of sight. So people being in the middle is not affecting those things as much. But again, this is like a big source of error that comes in, and we have to compensate for these using the other information that we have that I mentioned, maps, for example, routing information, and the sensors that come in. Yes.
Just so that I understand this heat map concept, on this, are you explicitly estimating what the APs are, or just purely predicting?
So this is the case that you know where the AP is. What I've shown here is you already know that the AP, for example, is here.
So you're not reducing that from the...
Not at this stage.
From the that you collected.
Oh, so so this is not. The point of this slide is not that. for the purpose of this slide, I'm assuming that you already know, either from the venue owner or through a process like you mentioned, from a learning process, you've established that the position of AP is here. And now, using the map information, so for example, if you look, there's line of sight here, right? There's like travel.
A little bit is a contradiction to what you said, which is having to survey a building.
Yes, that's
Because when you're getting the map of random buildings in the world off the internet is very easy. My cellar does that
sure.
24 hours a day.
Absolutely.
But figuring out where the APs are is that.
Yeah, so
I
that
think
part.
no building owner ever really knows that.
Yeah, so, but turns out that Cisco knows a lot more than some of the building owners know. And so there's in the, kind of organized deployments, like in most, enterprise kind of things, you really have that information, and Cisco uses it for their own, connectivity analysis and so on. And Qualcomm is actually partnering with Cisco in some of these situations. So you can get that information. And I mean, this is a different level of badness, if you like. It's really not.
Even though the building owner is disorganized, like Corey Hall,
Right.
they would still know, they can tell us where our APs are.
I don't know about Corey Hall in particular, but in most, like I said, enterprise scenarios, yeah, they have this information.
And then the idea is that the heat map is created through simulation.
So we have done. I mean, this is like there has been a process that you do it once and for all. I mean, you can repeat to refine the process, but so basically, for example, I tell you what we did. For example, for the type of office building that we use in Qualcomm is that we do a survey actually in one building of this type, and then we try to infer a model that based on the direct distance and number of walls and type of material and so on. Yeah, so you can get fancy that way, but it's at the level of it's the type of many of this thing. If you can remove the dependence on the the number of points on the map as opposed to just the type of material. If you can just for example adjust things, I mean you've reduced the problem by a lot. You can use the fact that, for example, this is line of sight, signal travels further at the same, strength as opposed to, for example, going through the thing. And this type of information you can infer from the map without knowing the type of material. You can adjust for it if you have that information coming in. But again, there's different levels of accuracy that you can get. You can always do a full survey at the end and just overwrite this whole thing, your a priori map with that. Yes?
This model is based on natural structural computing, based on professional space, structure like
It could, yeah. So, I mean, there's the type, yeah, I mean, for sure, the map of the building in general, I mean, it's not just it's just a complicated problem. I mean, it's like if you want to figure out the exact path the signal travels in a given scenario, there are a lot of things that you probably don't even imagine, right? But so there are a lot of factors that go into it. But to the first order or second order of accuracy that you're interested in, it's what we've seen is that the type of actually, like I was just mentioning, Qualcomm buildings in for example Santa Clara, we did some analysis on that and came up with a model that, depending on some parameters, including the ones that I mentioned, line of sight or not, how many walls and distance and so on, figures out forms this map. And then we take this same model and go to similar looking buildings, I mean office buildings. It's not like a completely different type of material probably. US has a building code, most people probably use the same material. But it turns out that it actually does pretty well in new buildings in terms of prediction, right? Which is not unexpected. If you really had different material, you can learn this a lot easier than learning the entire heat map by just adjusting the whole thing, for example, with the bias value or changing the couple of parameters that were out there.
Can you use the other access points to calibrate the map?
To calibrate the map,
So
sorry.
the fact that the attenuation may be different if the building is steel radius studs instead of width studs.
Sure.
It's way easy to sense that. You have multiple access points here. You can sense the signals between the two.
Oh, so between the two, you mean?
Yeah, between the two. So you
Right.
use other access points in the
Yeah. So there are studies of the sort that would require hardware level, AP to AP communication. And now that with the Theros in Qualcomm, people are thinking about those things. And actually, with you can actually, back to your question, you can actually enable the devices to learn their position, at least the ones that are close enough to the outdoors, by implementing having a GPS chip inside the access point that records, for example, that this guy is close to at this particular position. Start with some rough estimate of the position, which can be improved with over time with crowdsourcing. But yeah, if you have the communication between the access points, and people are, like I said, doing this different. Not just in Qualcomm. If I've seen academic papers with these ideas, you can definitely use that. Yeah. Okay, so similar thing for RSSI. There's this standard log decay type of form for the signal strength, and you can play with the parameters depending on the type of the building, and have a priori model for the ranging, or you can do, as before, heat map of the RSSI. And as I said, these are usually pretty good. There are some scenarios that things are off, and then you have to recover from this using the other information that you have. So if you have all of this, now you have these Wi-Fi models that essentially, like I said, translate a collection of measurements from different APs to a distribution over the map. It's easy to do, maximum likelihood estimate. Just evaluate this function at all the points over the map and find, the most likely points, or do like a least squared kind of estimate. So anyway, you can have like a single point estimate for the position. The problem, if any, is that you really are looking at it at a single instance of time. You're not using the past information. It's if there are problems with the model of the type that we were just talking about. Usually, these are very much local. They're depending on where you are, the type of model, by definition, actually, sometimes you're overestimating, some places you're underestimating. So, if you can track, the position over time, and if you can use the information, the measurements that you made beforehand to refine your position now, then you can correct a lot of these errors. And this comes, to the idea of basically estimating the trajectory as opposed to, just a single point. So instead of doing, a collection of point-to-point things that completely forgets about the past, we are looking at what is the most likely, given everything we've seen from this access point, and with the assumption that pedestrian user, for example, is taking this. What can you do now? What is the most likely position? What is the most likely trajectory that took you from there to here? So, the different levels of information that you can use. So the filter that you would use here obviously uses some assumptions about continuity of the motion. If you're moving, for example, what is the maximum speed that a pedestrian can move? What is, how likely it is that you're turning, and so on. So this is again, a cartoon example of a sequence of single point fixes in red. This is kind of the memoryless instantaneous things. And then I do a simple smoothing with some of the assumptions that I made. And that becomes the green thing. Now, there's no ground truth here, but it's, odds are, again, that the green thing is closer to the actual trajectory than the red is. Okay, so you can actually improve the type of filtering that you're doing if you have the map information, as I just mentioned. Map can give you some information about the movement of the device. movement of device held by the pedestrian user. So there are two types of information. One is feasibility. So for example, if you have map of this particular floor, fourth floor of Corey Hall, you know that, for example, even if your Wi-Fi model indicates that you're outside, then that cannot be. So you're essentially, by knowing the map and the positions and what is allowed and what is not allowed, you can eliminate some possibilities, and every time that you correctly eliminate some possibilities, you're improving your accuracy, and that's the kind of thing that you're trying to use. And the other source of information is actually the routing information, existence of walls and barriers. What is allowed, what transition is allowed and what's not, in a sense of, is it, can a pedestrian do it in a real scenario? So here's again an example just to illustrate this. This is like a snippet of a map of a building with the black lines being the walls. If you look at it without the map of the building, the transition from one end of the red point to the other is quite possible. It's like a couple of steps probably. But if as soon as you put in the constraints of the map, then this becomes an infeasible transition. If if the time between the two estimates were small enough, there's no way that the pedestrian would have moved from outside all the way to come back to that second point. So what you can do is that, again, to kind of give you the intuition behind this, is that if the sequence of measurements that you made beforehand, before coming to this point, indicated with high enough certainty that you're outside, you can definitely eliminate this point at the next instance. You just keep yourself in the corridor, and that's probably the right place. So these are the kind of information that you can use. Okay, so to get the map information, again, back to that problem of feasibility of processing these things. You don't want to have to go back and draw all these things by hand, or have somebody to process the maps and so on. What we did was come up with some automatic tools that start with pretty much any type of outline for the map of the building. Could be JPEG or AutoCAD or these kind of things, vector-based or pixel-based things. And what we do is try to infer all these information about the the routing and feasibility and these things automatically to the extent that is possible from the map. So and in the process actually simplify the problem. So the idea is that once you do this, if you do this beforehand, you don't have to do it in real time. And remember, all of this has to be done on the mobile. The calculation, you're talking about mobile-based positioning. So you want to simplify the process as much as possible on the device by having done it beforehand. So what we do is actually discretize the problem, like just overlay some grid. This particular grid that you're seeing is like a 2-foot grid that's overlaid on top of the map. Then what we do is, any edge, if I were able to zoom into this, but I guess maybe it's kind of more clear here. All the edges that cross one of the features of the map are eliminated. And this is done, again, in the pre-processing stage. So you can, spend some time to process one single map and then, send the consumed thing to the mobile. The next stage is to actually determine what is inside and outside. There are some, kind of heuristic algorithms to make sure that this is done. If you know a point inside of the map, you can pretty much, expand from it and cover the entire map and eliminate the points that are outside. This makes a lot more sense for the, for example, higher level floors, because you really want to eliminate the possibility that you're outside. So the next stage again is that you end up with ended up with a grid that's probably around like 10,000 points or so, quite a few points that you have to keep track. For the purposes of positioning, you really don't want to make it any coarser than this, because this, for example, this particular grid, which is 2 foot by 2 foot, as I mentioned, if you make it any coarser than this, your positioning ability suffers. You're quantizing to something that's adding to the inaccuracy of the system. But for the purposes of routing, you really don't want to have to do routing on the entire thing. There are some other algorithms that we developed to that in stages it tries to absorb points and just essentially reduce the complexity of this map to a point that it becomes just like a skeleton covering this thing. And we use this more simplified map with like a few hundred points at most for routing purposes, and we do positioning on the finer grained things. So it's like a combined solution. And all of this thing again is done in the pre-processing, so you end up with kind of like a little bit of a good trade-off between the size of the assistance data and the accuracy that you get out of the system. Okay, so the next component is the sensor measurements. Like I mentioned, most of the smartphones these days have these commercial grade sensors available on them: 3-axis accelerometer, gyroscope, and magnetometer at least. Barometer is coming in the next generation of things, and you can use that one too. So what we want to do is to be able to use this information to get odometry measurements, essentially tell how you're moving, if you're moving, how fast you're moving, and which direction as far as possible. If you have all of this thing, you can put it together with the mobility model that we were just talking about and improve the accuracy of the system. So it turns out that actually doing kind of complete inertial navigation using these measurements, sensor measurements, is really not practical, at least with both because of the inaccuracies of the sensor measurements that you're getting. It's not like high quality sensors that go into commercial phones, and also because of the fact that as opposed to, for example, the case that a sensor is mounted on a car with like non-holonomic, for example, constraints and so on, you really don't have any of those constraints. The device can be held in hand, and most typically you just shuffle it around and you change direction and so on. So if you try to do the natural thing with double integration of accelerometer and gyroscope and those things, you end up with huge biases. In fact, for the accelerometer in particular, there's this big component of gravity that's always there. So if you try to, a tiny bit of error in estimating direction of gravity completely messes you up. The linear acceleration you're trying to measure is in the margins of, that huge component from gravity. So what we do to robustify this problem is break up the problem into, a combination of a pedometer, which it's again this like it's not you're not doing like a instantaneous movement. You're doing a pedometer that figures out the events of step events, as well as estimating the stride length, as well as another component, which is the heading filter, which tries to estimate which direction you're going. This again is not an easy problem. If you think about it, the device that you're holding in hand, from magnetometer and accelerometer gravity sensor, you can determine the pose of the device, but that doesn't tell you which direction you're going. I could have hold the device and go this way or that way. So it's really you need to look at the inertial aspect of this. There are some tricks that we're doing there to try to get that information, but it's a hard problem. It gives you, there's no way that you can get, quality pedestrian dead reckoning just based on accelerometer and just based on sensors. What we do instead is we look at some, again, probabilistic estimates here. We're looking at the distribution over so sometimes, for example, based on the method you're using, you're pretty sure that you're moving in a 45-degree span of directions. And if you have other constraints, for example, there's a corridor that you're either going this way or that way, obviously this is enough. But if you don't have it, then the errors are cumulative because of the fact that this is incremental motion. So in any case, we are putting all of this stuff together in a probabilistic sense. The distribution is coming out here, and a particle filter is used here. I'll talk about it in a little bit. The reason we ended up using the particle filter is that as opposed to, for example, a Kalman filter or anything of the sort, is that the type of constraints and information we are using is highly nonlinear, highly discontinuous from time to time. In the example I showed, one side of the wall, there's going to be like a sharp drop in the distribution at the location of the wall. You just cannot, do this with the Gaussian assumption of the Kalman filter and so on.
Can you kind of how you get stride distance?
Yeah, so that part is kind of like a little bit of heuristic-based thing. It turns out that there's a correlation between stride length and frequency of steps. So, the faster you go, the higher frequency your steps are, the longer strides you're making. So there's like a model to fit there. It also depends on the height of the user and all kinds of other things. But the first order, if for example, device is associated with a particular person, that part can be learned at a couple of parameters that correlates the stride length with stride frequency. So it's actually you can do better than just fixed stride.
Right. You can occasionally get a bearing from some other source and calibrate that.
Yes, absolutely.
Estimate also.
That's absolutely true. Yeah, actually, to the point that a few years ago, I was in one of these location conferences, and there was a paper on correlation between season and stride length. So it turns out that in winter, for example, people take smaller strides, and summer they just go. In any case, there are all kinds of you can infer a lot of correlations. Yes.
Use the magnetometer for heading?
Yeah, you have. So you basically to get the orientation of the device, you can't avoid using the magnetometer. If you had the original estimate, you could use the gyro to figure out the relative turn and so on. But magnetometer is you have to use it in the indoor environment. There's a lot of sources for interference with magnetic things, but those things can be properly modeled and so on. But in most places, they can. Yeah, so there's like auto calibration is so it's so if you start with a good calibration for the device, you can. If you walk, for example, across this straight line, depending on how close you are to magnetic source of interference, there's going to be like anomalies that come locally. But then, if you're moving, you can figure these out. If you look, so what I mean is that it gives you some estimate of orientation. And again, to emphasize, we're looking at all pieces of information. We're trying to put everything together. So, for example, existence of the map will be able to. When you have the map constraints, you can afford to have some noisy estimates of the. So it's a delicate balance, right? So it's actually the question comes up: what if the map has changed and so on? So you have to combine these in a way that makes sense, and that's what we're trying to do. Yes.
Why couldn't you just learn?
You could learn the map. It's you mean from the movements of people or from? Yeah. So absolutely. Yeah. So that's another aspect that can be done. That's like a crowdsourcing aspect of things. We're not doing it just because we're starting with something that's simpler, but yeah. So it can be done. Okay. So then the last part, the part that integrates all of these things, I mentioned. So let me actually. Say a couple of words about what the particle filter is, in case anybody's not familiar with it. It's basically Monte Carlo based simulation to keep track of the distribution of the positions or any set of any points in the state space that you're interested in a way that each particle basically keeps track of one scenario in one possibility in the world. And the idea is that the frequency of the particles represents the weights of that possibility or that region of possibilities. Now you're discretizing the problem in a way that instead of having representation at every single point, you're discretizing your state space for this to make any sense. And as I mentioned, we are using things on top of that grid, which enables us to do this in real time. But in any case, for this to work, you really have to have some continuity and smoothness over the location of, the distribution value based on the location. So as I mentioned, each particle represents one possibility, and then the number of particles represents the frequency, or rather the amplitude of the the distribution at that vicinity of points. And what is critical here is that you want to have enough particles, enough representatives, so that pretty much all meaningful possibilities are covered, at least by some particles. So the danger is that if you have too few particles, then some possibilities that may actually be the correct state of the world may not be represented, and then those things will propagate, especially when you have these hard constraints on the position. So people have been using particle filters for robot localizations. What is the challenge here is to have a simple enough version of this that gives you the advantages of using the constraints, but is also simple enough that can be run on a mobile device. So the steps that are involved in a particle filtering are the following. First, you start by you start with some original cloud of particles representing your original distribution. This can be done based on the single point fix from the Wi-Fi position or any other source of information that you had. If you just entered the building from outdoors, for example, you might know that you're somewhere in the vicinity of the entrance and so on. Then you use the information from inertial sensors, like I mentioned, odometry, or any other constraints that you have from the map to propagate these particles. So, for example, if you knew that there were 2 steps were taken in that vicinity of directions, you can propagate these things according to the weight that you're giving to that distribution. Some of them will go this way, some of them will go that way, and so on. So the idea is that this will represent the a priori distribution before making the actual Wi-Fi measurements, and based on the previous information that you had. Next thing you do is you actually make the measurements and you weight each particle, in this case based on their position. You could have some correlation with, for example, velocity and so on, if there is such thing. And you weight each particle, again, based on how likely it is that the measurements that you just made were made at that point. And then the last step is to resample from this crowd of particles with their weights to the number that you want, so that you have a kind of a posterior, at this case, of that takes in both the information from the Wi-Fi measurements that you made in terms of the weights, as well as the prior, which is just the frequency of the particles at each position. Okay, so putting this all together, this is again a simple demonstration of this thing. I'll talk about it in a little bit. This is the system working in one of the Qualcomm buildings. What you see here is the yellow dots are the particles. The blue line is the sequence of estimates. The green thing that you see is actually the ground truth that we established through a different mechanism. And you occasionally see these red things, red crosses. Those are the possibilities that are eliminated while crossing some barrier of the map. Okay, so as you can see, the combined solution, I could have shown you this without the inertial sensors, and that gives like quite a bit of more problem. So what you see here is, the kind of zigzaggy situation is because of the fact that the Wi-Fi, for example, was strongly pulling you in here, and in this particular case, there is a route that goes from up there coming down. So there's some scenarios that you end up having error, because especially if the entrance is at the wrong place, and so basically the map information does not eliminate the wrong information you're getting from the Wi-Fi. Similar situation there. Okay. So This thing is actually implemented in, this is actually what I'll show next is kind of a demo application running on a commercial phone. This particular thing is based on RSSI only as well as maps. So we are using order of a few hundred particles, and because of the fact that we are pre-processing the map, the propagation is really simple. You really are constrained on top of this grid. So you really, as opposed to the traditional particle filters that you use, that you have to determine in real time any possible path and figure out whether this is possible or not. Here we're constraining things, and that simplifies things quite a bit. So it's perfectly, manageable in a medium smartphone, basically. Okay, so this is a situation that person is walking along the corridors, and this particular thing is again a little bit old from last year. Actually, there's better GUI right now. This is doing both locationing as well as navigation in real time, and just to kind of show you the type of application that would be enabled with this. And okay, so this is another thing that came up at corporate R&D in Qualcomm. We have this demo day usually that people just different groups go and show their, showcase their project that they're doing. And this particular Pac-Man thing came up as a kind of afterthought, very close to the time that there was a demo thing. The idea came up to just enable, kind of an application like this. Some virtual items are on the map, and the person is given the device, and by walking around, they can collect these things. And turned out to be quite popular. And actually, there's some other, companies like Disney and so on were sounded some interest in this. So in any case, there is some. You can imagine, the kind of application that very quickly will be enabled when you have this kind of technology. Okay, so. Yeah, so this guy goes on and collects all the pellets. Okay, so that's basically it. So I'm just going to wrap up. So the summary was, the kind of information that we're using: Wi-Fi measurements, building map, sensor measurements, and the particle filter. There's a lot more detail in each one of these things, just to make it both, practical in terms of accuracy and, complexity-wise, so that it can be run on a device. Yes. Thank you.
So it's a bit curious that do you have a mechanism where the user can actually sort of plug in some information? I might just know I'm in front of not.
Yeah, you can. So that's this. It doesn't exist in this particular version of this thing, but absolutely. So I mean, basically, there's some other. Maybe I'll just mention some of the things that people are looking at either at Qualcomm or different places. So. Related to what you just said, there's a possibility that, for example, you can point the camera at the place, and you're in trouble. You have no idea. The estimate is off. It's possible to just turn on, point the camera, get a overview of the place, and if you see, for example, whatever store right in front of you, you can just match it against the database of these things. Or you can have, like you say, some kind of forced input from the user that corrects this thing. But yeah, so it doesn't exist in this, but for sure you can do this.
So have you looked at peer-to-peer communication between
The idea has come up. You haven't implemented it, but yeah. So you can definitely. That's another thing that you can actually kind of extend by, if you can figure out the topology of like the position of the maps of the different users relative to each other, and you have a couple of fixed points. Obviously, you can do a lot better than that. Yes.
It seems like you've used most of the sensors which are available on a cell phone. I was curious as to how useful the ambient light sensor information might be. Have you guys looked into that?
It's again, many of these, as I said, there's like 4 years this project has been going on, and ideas have come up. It hasn't gone into the process. I mean, there are people who are doing. I'll tell you, like, another interesting thing is that people are doing kind of sound-based things. So, for example, not just ambient sound, but also along the lines of peer-to-peer thing. If you have two devices recording something, turns out that if you're close to each other, obviously you're recording the same sound signature. Same thing with ambient light and so on. If there's variation, of course, you can correlate these things and infer proximity and so on. So there's a lot of things that you can do, but it's not in the prototype that we are
But it
building.
seems like there's a very rich body of literature that says what the ambient lighting in a building is supposed to be on like a sunny day or a cloudy day, or that could potentially give you much more information.
Yeah, you can. So I'll just have to warn you that it's not just indoor and outdoor distinction, right? The question becomes, is that going to be good enough to distinguish, for example, like this point versus 3 meters that way, or this room from that room? So the kind of information we are trying to infer is like a lot finer grain than just indoor and outdoor. You could infer something from like a conference room versus somewhere close to the thing, but it becomes tricky. Yes.
A little bit complicated video using, for example, Google Glass, which has the camera going on at all times, and using that for determining location.
So with the sequence of frames, you can do what it helps quite a bit is with the movement. You can what you can't do as well with inertial sensors because of the issues that I mentioned. If you had, for example, if you can track features in a sequence of frames, then you can figure out the direction of the movement, and that comes into that can be used. Or you can use individual frames with some frequency and try to infer the location from individual ones. But like I said, what would make sense from a video frame is to figure out the direction of movement and how fast you're moving. And yeah, those things can be used. But again, there's a lot more that can be done than has been done, as you can imagine. It's basically the idea has been here to come up with a solution that's reasonable. And actually, I'll just mention in a second that this work has been actually commercial. It is being commercialized as we speak. Qualcomm is having this system, they are on plan to enable hundreds of venues by the end of this year, and basically commercialize this under like a commercial name. It's called ISAT. There's a little bit of a corny video associated with it, but I'll just quickly put this on as I'll wrap up. So a lot of aspects to this thing. I'll just skip over, and this is I'll just have this very quickly. As we wind down, I'm actually not going to have a lot of. So this is again a product that is being commercialized. With somebody from with my own background, I research in theoretical electrical engineering and so on. It's actually quite interesting to have come after a few years to a point that they're actually building this. Whatever you're doing is hopefully is going to be popular and people will use it. But yeah, that's
providing end-to-end platform capabilities.
Great. Well, thank you.
Where's my appointment?
So we'll be around for a few minutes if people want to talk. So maybe what we'll do is, instead of taking more questions because some people have to go, is he'll be here. Come on up and feel free to chat.
Where my ride is at.